nucleus. So if you change the number of protons by one, you've changed one element into another element, right? That by definition is alchemy. You know, the big dream of the alchemists in the past, to change lead into gold. Well, with nuclear physics, you can do that kind of thing. I mean, you know, at tiny amounts, but you know, that's alchemy. All right. How about what's the expectation value of 1 over r? And you may ask, why is that useful? Well, this featured in Bohr, B-O-H-R, Bohr's theory. And so if you plug 1 over r into, instead of having r here, you have 1 over r. You can calculate that integral, and you'll get 1 over a naught. Right? Again, homework. Right? So now 1 over r, that's proportional to the potential energy. So the potential energy expectation is this. You know, again, homework. And that agrees with the Bohr theory. Okay, so very nice. So Bohr was very happy, because he's watching all this development occur in the 20s and 30s, mostly, well, yeah, 20s, 30s. So he was very happy to see his old ideas from 1913 come true, and more than that, I mean, the theory made Bohr's ideas look rather primitive, because Bohr was just sort of guessing a bit, combining classical properties with quantized properties, and it was a big mishmash, a mix of both, and you know, a bit of the old world and a bit of the new world, and not terribly consistent. But quantum theory made it much more consistent, relatively speaking. You actually get on courses on interpretation of quantum mechanics, and then the sparks will really fly. But it'll be fun. But you'll have to wait a few years. I have to get through the core, meaning the principle, the most important courses first. So the philosophy will have to wait a bit, I'm afraid. You'll have to be patient for quite a few years. Okay. Okay, so next topic in this rag bag of chapter. The idea of a free particle. Free in what sense? Well, it's a particle that's subject to no potential. So the V is naught. There's no electric field there. There's no magnetic field, gravitational field, or it's just free. It does what it likes. So that means the STI, Schrödinger time-dependent equation. The V term in this equation drops out because it's 0. So you just got this, right? So we've seen stuff like this before, and we usually said the U took the form of A sine plus B cos. Remember? In this case, well, you can rewrite sine and cosine in an exponential complex number form. So this is just an alternative way of your A sine plus B cos, right? And x here can, well, yeah, it's totally free, right? It can be anywhere. This is for a specific k, right? This k is defined as this, right? And for a specific energy, your k is known. Now, can you remember? Oh gosh, an early lecture in this course. We split the wave function that originally is a function of position and time into two parts. U, the part depending on space, and another part depending on time. And the part like UF, little f, and little f is exponential minus I, square root minus 1, ET over h bar. Okay? So your U here is this, so plug that in. Okay? Now rewrite this a little bit as this way, so you take the I out in common, so you get now kx. Now k is the wave number. So from the de Broglie relation, remember, P P equals h bar, is that right? P equals h bar k. So the h bar is cancelled over the k. So k is equal to P over h bar. So that's where this comes from, and that's just written in this form. Now your E here is from E from this you can calculate what your E is, and so you get this sort of form, right? So that's the sort of general form for a wave function that is free. Okay, meaning no potential, no potential acting on it, in a sense constraining it. Just does what it likes. Now, except for the constraint that the energy, the Z, is positive, there's no restriction otherwise, right? So that means these E's here are not quantized. Okay. So for a free particle, you do not have quantized energies, and that means the energy levels. Well, level's the right word, but the energy values that this free particle can have is continuous, right? It can have any energy value, well, positive. Okay. So these wave functions, physically, what's going on? What are they? How do you visualize, if that's possible, the wave function that has this form? What is it? Well, it's anything that's exponential I something tends to be an oscillation of some sort, right? This has the form of a wave. Looks like the solution to a wave equation, right? We talked about that when we were talking about Schrodinger's ideas, and especially de Broglie's ideas. Okay, so look on this as a wave that's traveling to the right. Okay, well, just a convention. If k is positive, and it's traveling to the left if k is negative. That's just the convention. All right, and so in other words, infinite waves, they just go on forever. Now, so you have this wave of sort of like infinite length. Now that which is consistent with this. Now that's also consistent with the Heisenberg uncertainty principle, because if your k, if you know k exactly, then you know the momentum exactly. Therefore, the uncertainty in the momentum, your delta p is 0. Delta p is 0 because there's no uncertainty in the momentum because you know p and hence you know k exactly. And so your delta p is 0. Well, that implies from the Heisenberg uncertainty principle that your delta x, your uncertainty in the position, is infinite. Well, if you have this wavicle that's extended to infinity, right? It's just infinite length. You haven't a clue where the particle is because its wave, in a sense, is just everywhere. So delta x is infinity. So that makes sense. But you've got another problem. How do you normalize a function like this? So the particle's got to be somewhere, right, in that huge wave. But so how do you normalize the thing such that the probability density, you just square this to get probability density, integrate over all possible distance. We're talking one-dimensional system here, so over all x, if you like, from minus infinity to plus infinity, minus infinity dx, and but if you square this, you get a constant. So if you're integrating over a constant, you just get infinity. Problem, right? So we've got a conceptual problem here. This model of a wave, if you like, for a free particle is giving us an infinity problem when we try to normalize. So we've got a problem. So what do? We have to go back to the drawing board and rethink. We have to change the models or something. Well, so in practice, your delta x here is not completely unknown. Like your particle presumably is somewhere in the lab, the laboratory where you're working, right? So your delta x won't be infinity. It'll be, I don't know, meters or something at least. Right? So assume it's there. So your model of a free particle is just a wave with the exact k, exact momentum, is probably not accurate. So physicists compromise, and then they talk about, instead of just a wave, they talk about a wave packet, like a bundle of waves. And what does that mean? It just means a superposition. So you're adding waves of slightly, in each one, slightly different momentum, de Broglie momentum, or in other words, slightly different values of k. So you have a bunch of these waves, and you just add them, superpose. You can add waves, and if you have a range of momenta of k values for these waves, you can add them up in such a way that you get a sort of like a wave packet, the sum of these waves, which has a certain delta p, an uncertainty in the momentum, the spread of the momentum in your packet, and by adding these waves with different k's, you can do that in such a way that your delta x becomes, an uncertainty position. It then becomes fairly narrow, right? Instead of being hugely spread out, it sort of becomes like this. So you then get a delta x delta p, of course, consistent with Heisenberg uncertainty principle. But your delta x then is fairly narrow. It's not like huge. So by modeling the free particle as a wave packet, an addition of waves with varying k values, varying momentum, then you can get a delta x that's not too spread out, right? So hence a wave packet. Okay. That's the end of the board again. Now tomorrow I will buy the new board. Maybe in the evening. So that means nowadays typically, now that the upload speed to YouTube has been halved, I'm doing pretty consistently now 3 sessions a day, two in the afternoon, more or less with light. The first one nearly always with light, daylight. Second one, compromise. Third one always in the evening, just time factors. So perhaps the new board will be with the 3rd session tomorrow. So expect changes, big changes, huge. The board is 2.4 meters long, right? So it's the length of 3 of these bookcases, which are each 80 centimeters wide. All right, so I'll stop there till next session.